Now, we are going to discuss our 45 problem assignment on this topic, atoms and nuclei, the 18th unit of your crash course program. The first problem is very simple. It is from 2009 AIPMT. In a Rutherford scattering experiment, when a projectile of charge Z1 and mass m1 approaches a target nucleus of charge Z2 and mass m2, the distance of closest approach is r0. The energy of projectile is, we know that it is due to repulsion between charge, and repulsion is directly proportional to product of charges. One charge is Z1, another is Z2, so it should be directly proportional to Z1, Z2. We have complete derivation in Adams' slides. Next, it is from 1989 AIPMT. To explain his theory, Bohr used quantization of angular momentum. कि angular momentum of electron in any orbit is an integral multiple of h upon 2 pi. So, we are going with B option. Consider an electron in the nth orbit of a hydrogen atom in the Bohr model. The circumference of the orbit can be expressed in terms of de Broglie wavelength. We know that according to Bohr, angular momentum is an integral multiple of h upon 2 pi. h upon 2 pi. And what is circumference? Circumference is 2 pi r. Take 2 pi on this side. So, 2 pi r is equals to n h upon mv. mv means momentum and h upon p is lambda. So, what we are getting? 2 pi r is equals to n lambda. So, we will go with option D. Next, it is from 1992 AIPMT. It is from 1992 AIPMT. In terms of Bohr radius r0, the radius of the second Bohr orbit of hydrogen atom is given by, I told you in derivation that this type of problems are very important, and we have complete derivation before starting these problems. R was proportional to, in orbit R was proportional to n square by z. We are talking about only hydrogen, so z is 1. R is proportional to n square. If you move to second orbit, means R is equals to some constant into n square. For first orbit, it is k into 1, means k. They are saying radius of first orbit is r0. For second orbit, n is 2, means 4k. It means it should be 4 r0. So, we are going with A option. We are going with A option. Now, fifth problem. When a hydrogen atom is raised from the ground state to an excited state, what will happen? It will raised from ground state. In ground state, it has less energy. So, when it will get energy from outside, it will go to high energy level. So, potential energy will increase, but we know that velocity was inversely proportional to n. So, velocity decreases means kinetic energy will decrease. So, we will go with option A. Next, it is from 1996. According to Bohr's principle, the relation between, we just discussed in previous problem, R is proportional to n square. So, for 6 we will go with answer D. When hydrogen atom is in the first excited state level, its radius is Bohr radius means radius of first orbit. So in first orbit, if its radius is r naught, r is proportional to n square. So for second orbit, it should be 4 times the first orbit. It should be 4 times the first orbit. Just we have completed this derivation. So we will go with option B. In the Bohr model of a hydrogen atom, it is from 1998 AIPMT. The centripetal force is furnished by the Coulomb attraction. We know that between the proton and electron, if A naught is the radius of the ground state orbit, m is the mass, E is the charge on the electron, and epsilon naught is the vacuum permittivity. The speed of the electron is, we have derivation there, कि you will get centripetal force. They are talking about this. What they are saying, A naught is the radius of ground state, A naught, mv square upon r, from attraction between electron and proton means E square divided by A naught square, cancel one A naught. So what we are getting, V square is equals to E square upon 4 pi epsilon naught A naught m. So what is V? V should be E upon square root of 4 pi epsilon naught A naught m. So we will go with option C. 8th C option. So now we are doing 9th problem. The energy of hydrogen atom in nth orbit is En. The energy in nth orbit of singly ionized helium atom will be, since energy is directly proportional to z square by n square. For hydrogen atom, K, for hydrogen Z is 1, so it is K by n square. For helium, Z is 2He4. What we are getting? A hydrogen atom 1H2, helium 2He4. So hydrogen atom Z was 1, for helium atom Z is 2. So what we are getting? It is 4 divided by K into 4 divided by n square. But what is K by n square? It is EH2. So what we are getting? 4 EH2. So we will go with A option. 10th. In which of the following system will the radius of the first orbit will be minimum? It is from 2003 AIPMT. We know that Rn, radius of nth orbit, is proportional to n square upon z. N is same for all atoms. They are saying n is equals to 1. We want to talk first orbit. Minimum, if z is minimum, z is maximum, then Rn will be minimum. So z should be maximum for minimum R. And maximum atomic number is with lithium. So we are going with A. So 10th A. Now it is from 2004 AIPMT. The Bohr model of atom A assumes that the angular momentum of electrons is quantized. Yes. So we will go with option A, the main postulate of Bohr's theory. Now it is from 2005 AIPMT. the total energy of an electron in the first excited state of the hydrogen atom is minus 3.4 electron volt. Its kinetic energy, we discussed in starting, kinetic energy in any orbit is equals to modulus of total energy. So what is total energy? Remove the sign, you will get kinetic energy, means 3.4 electron volt. So answer of 12th problem was A. Now it is from 1988 AIPMT. The ionization energy of hydrogen atom is 13.6 electron volt. The ionization energy of a singly ionized helium atom would be, we know that energy is proportional to Z square, and for helium Z is 2. 2 square means 4. So for helium it should be 4 times than hydrogen. So if it is 13.6 for hydrogen, 13.6 into 4, 54.4. So we will go with option D. 13th D. 14th. It is from 1991 AIPMT. The ground state energy of hydrogen atom is 13.6 electron volt. The ionization of hydrogen atom from its second excited state. Second excited state means electrons are in third orbit and energy is proportional to Z square by N square. It means for particular atom, product of E and N square should be constant. We know that in first orbit, E was minus 13.6 electron volt. In the third orbit, it should be minus E into 3 square means 9. So energy of electron in second excited state means third orbit, it is minus 1.51 electron volt. So to ionize atom from this stage, you need plus 1.51 electron volt energy. To remove electron from this position, so we are going with option A. So for 14th, option A is correct. 15th, it is from 1992 AIPMT. The ionization energy of hydrogen atom is 13.6 electron volt. The energy corresponding to a transition between the third and the fourth orbit is, ionization energy means energy to remove electron from first orbit. It means in first orbit energy is minus 13.6 electron volt, and we know that energy is directly proportional to Z square by N square. So for particular atom, E into N square should be constant. So if you want to calculate third orbit energy, so E3 into 3 square 9, it should be E1 into 1 square means minus 13.6. This implies E into N square should be constant. For first orbit, E1 into 1 square is equals to minus 13.6. So in third orbit, energy is 1.51 electron volt. For fourth orbit, it is minus 13.6 by 16 means minus 0.5 0.85 electron volt. So when transition between third and fourth orbit, it should be difference of these from third and fourth orbit. Delta E should be minus 0.85 minus plus 1.51. So you will get 0.66 electron volt. So we will go with option D. 15th D. 16th, it is from 1996 AIPMT. The energy of a hydrogen atom in its ground state is minus 13.6 electron volt. The energy of the level corresponding to the quantum number n is equals to 2 in the hydrogen atom is E is proportional to Z square by n square. For first orbit, it is minus 13.6. For second orbit, it should be, suppose energy is E into 2 square means 4, so E should be minus 3.4 electron volt. So we will go with option D. So 16th correct option was D. Now it is from 1997 AIPMT. The energy of a ground electronic state of hydrogen atom is minus 13.6 electron volt. The energy of the first excited state, it means electrons are in second orbit. So for E2, it should be minus 13.6 upon 2 square. So minus 3.4 electron volt. So we will go with option C. 18th, it is from 2000. Maximum frequency of emission is obtained from the transition. We know that delta E, it should be maximum. Frequency maximum means energy maximum. So what is the energy in first orbit? We are talking about a particular element. So energy is proportional to 1 upon n square. N means E is proportional to, we know that exact formula is this, E is proportional to Z square by n square. For particular element, E is proportional to 1 upon n square. E is equals to K upon n square. So we are dealing with 1, 2 and 6. So energy in first orbit minus, energy is negative in each orbit and it is the number on which it depends. So minus for first orbit K upon 1 square. For 2 minus K by 4. For 3 minus. For 6 minus K by 36. So when it is coming from second orbit to first, delta E we will get in case of A. N is equals to 2 to N is equals to 1. Final energy is minus K. Initially it was minus K by 4. So what we are getting? Minus k plus k by 4. In first, from second to first, first is final and second was initial. So we are getting minus 3k by 4. K by 4 and minus k. In B option, 6 to 2. Final is 2. Initially n was 6. 2 means minus k by 4. Minus plus k by 36. Minus 9 plus 1. Minus 8 by 36k. For C, 1 to 2, final is 2. Initially it was 1. So in 2 minus k by 4. Minus plus k. 3k by 4. D. N is equals to 2 to n is equals to 6. 6 to 2, it was minus, so it will become plus 8k by 36. So all energy we have with us. Which is the maximum? It is minus 0.75 k. So maximum is minus 0.75 k. For B, maximum frequency of emission. So when it is coming from 6 to 2, higher energy level to low energy level, it will emit the energy from where it is coming. From higher energy level, it has higher energy in that orbit. In 6th orbit, what we have the actually relation, in this it is coming from second to first, and it is coming from 6th to second, and it is going from first to second. Lower energy level to higher energy level, it will not emit. In case of C, it will not emit because it is going from low energy level to high. In D, it will not emit. Emission is only in 2 cases. When it is coming from second to first, or it is coming from 6th to second. It is coming from second to first. See, example we are taking of hydrogen atom. In ground state, its energy is minus 13.6 electron volt in 1. In 2, it has minus 3.4 divided by 4. In 6th, it has minus 13.6 upon 6 square means 36. 6 square means 36. So what we are getting? The energy is in 6th orbit minus 13.6 divided by 36 means minus 0.377. So when it will jump from second to first, it will delta E from second to first. Minus 3.4. What is the excess amount? It is in second orbit, it is in first orbit. Excess amount was 10.2 electron volt. When it is coming from 6th to 2nd, what is excess energy? In 6th energy is minus 0.377 plus in second it was minus 3.4. It is emitting minus 0.377 plus 3.4. So, we will get nearly 3 electron volt. Clearly, when it is jumping from second to 1, it will emit highest energy in these two cases. High energy means high frequency. Energy is H into nu. So, what we will get? We will get high energy in the option A. So, we will go for option A. Next, it is 2 times they asked, once in a 1990 AIPMT, after that in 2005, after 15 years again they repeat the same problem. Energy levels A, B and C of a certain atom corresponding to increasing values of energy means low energy level A, high energy level B, after that third energy level was C. Lambda 1, lambda 2 and lambda 3 are the wavelengths of radiations corresponding to the transition C to B. Lambda 1, C to B. Lambda 2, B to A. Lambda 3, C to A. Means when it will come from C to A, it will emit an energy EC minus EA, difference of these two energy level, means difference of this plus difference of this. We can write this energy level difference between EC minus EB plus energy difference between AB and EA. When it is coming from EC to EA, emission is of wavelength lambda 3, but energy is Hc by lambda. It should be this. When coming from C to B, lambda 1 means Hc by lambda 1. Coming from B to A means lambda 2, Hc by lambda 2. So, what we are getting? 1 upon lambda 3 is equals to 1 upon lambda 1 plus 1 upon lambda 2. Take LCM, lambda 1 plus lambda 2 by lambda 1 into lambda 2 means lambda 3 is equals to lambda 1 into lambda 2 upon lambda 1 plus lambda 2. So, we will go with option B. Next, it is from 2007 AIPMT. The total energy of electron in the ground state of hydrogen atom is minus 13.6 electron volt. The kinetic energy of an electron in the first excited state means second orbit, and energy in second orbit, we know that it should be upon n square means 2 square. So, it is minus 3.4 electron volt. So, total energy in first excited state is this, and kinetic energy in this, we know that modulus of total energy. So, remove the minus sign. What we are getting? 3.4 electron volt. So, we are going with D option. Next, it is from 2008 AIPMT. The ground state energy of hydrogen atom is minus 13.6 electron volt. When its electron is in its first excited state, just we solve. First excited state means second orbit. Its energy at this place, it should be equal to minus 3.4 electron volt. It means electrons which are orbiting in second orbit have negative total energy of 3.4 electron volt. If you want to remove electron from this state, it is what we need when its electron is in the first excited state. Its excitation energy means what energy you need to take electron from ground state to this, means difference of these two. We are not want ionization energy, we want excitation energy. Excitation energy means energy needed to take electron from ground state to that state, means energy difference between that two energy levels. So excitation energy should be difference of these two energy levels. So minus 3.4 plus minus plus is 10.2 electron volt. So we are going with A. If they are asking you what is the ionization energy from this stage, then we will go with plus 3.4 electron volt. Next, it is from 1993. Hydrogen atoms are excited from ground state to the principal quantum number 4. Means atom is in fourth orbit. It is fourth orbit. Third. It is second. It is first. So, which type of energy emissions are possible? How many wavelengths are possible? If we are talking from fourth to third, you will get one spectral line. Fourth to second, you will get second spectral line. From fourth to first, this energy difference will give you third spectral line. Or from third to second, one spectral line, fourth. Third to first, next spectral line. From second to first, last spectral line. So we are getting total 1, 2, 3, 4, 5, 6 spectral lines. Or if you are in principal quantum number n, number of spectrum lines you also can calculate by n into n minus 1 by 2. In this case, n was 4. So 4 into 4 minus 1 by 2 means 2 into 3. In this way also you can calculate number. Means if atom is in the excited state of principal quantum number 6, how many spectral lines are possible? 6th means n is 6. 6 into 5 by 2 means 15. Next, the figure indicates the energy level diagram of an atom and the origin of 6 spectral lines in emission. Which of the following spectral line will also occur in the absorption spectrum? The absorption lines are obtained only when the electrons jumps from ground state to higher energy level. So if it is jumping from ground state, only 3 higher energy level are possible here. From first it can go to second. From first it can go to third. From first it can go to fourth. So first to means X to C, you will get 1. X2 from ground state to higher energy level. So X to C, X to B or X to A. only 3 absorption lines are possible. X to C means corresponding to 1. X to B means corresponding to 2. X to C means corresponding to, X to A means corresponding to 3. So we will go with option 3. Next, it is from 1995 AIPMT. An electron makes a transition from orbit n is equals to 4 to the orbit n is equals to 2 of a hydrogen atom. What is the wavelength of the emitted radiation? We know that what was the formula for energy? The formula for energy in the nth orbit, we have complete derivation 1 upon lambda r and f final stage square minus 1 upon ni square. Orbit 4, it is coming from 4 to 2. So R 4 means 1 upon 4 to 2. Final is 2, so 2 square is 4. Initially it was in 4th. Take LCM. It is 4 by 16 minus 1 by 16, 5 by 16. So lambda should be equal to 16 by 5 R. 4 minus 1, 4 by 16, 4 minus 1, 3. It is 3, 3. So it is 3R. So we will go with option D, 16 by 3R. 25th, it is from 1998 AIPMT. The 21 centimeter radio wave means wavelength 21 centimeter emitted by hydrogen in interstellar space is due to the interaction called the hyperfine interaction in atomic hydrogen. The energy of emitted wave is, wavelength is given, you can calculate energy. Only one formula is there, hc by lambda. What is h? 6.63 10 to the power minus 34. What is c? 3 into 10 to the power 8. What is lambda? Lambda is 21 centimeter. Centimeter means 10 to the power minus 2 meter. 3 sevens are, table of 7 is easy. 7 nines are 63. 33. 7 fours are 28. So 0.94 into 10 to the power minus 34 and 10 minus 24 joule. 0.94 is nearly 1. So we can say 10 to the power minus 24 joule. So we will go with option D. So D was correct. It was the problem from 1998 AIPMT.